today's program, I'll have to treat test for the presence of heteroscedasticity in a regression model. And the test we are to treat here or in today's program is the pack test. The pack test. Okay. All right. So, all right. When we want to test if there exists if there exists unequal variance in the error term of a regression model, there are many tests. Okay. We can use the white test, the pack test, the glitter test, etc. All right. But in today's program, I have to treat the pack test. Okay. So, like I said before, I said that the pack test is a test in which we can use to verify if there exists the problem of what? Heteroscedasticity in a regression model, or if there exists a variability in the variance of the error term of a regression model. All right. Now, so that the test expresses the variance of the error term as some function of the independent variable. All right. So that the test expresses the variance of the error term or stochastic term as some function of the regressor. As a function of the regressor or independent variable. That is sigma I squared equals to f of xi. Okay? That is sigma I. All right? Okay. Sigma I squared. All right. Okay. Equal to f of xi. Okay. So I say that the test expresses the variance of the error term. Okay. The variance of the error term as some function of the regressor. That is sigma I squared equals to f of xi. In this case, this equation, all right, that we have established, okay, shows that the variability in the variance of the error term, okay, is a function of the predictor variable. That is sigma I squared equals to what? F of xi. All right. So, it further suggests, the test further suggests that sigma all right, further suggests that sigma I squared, we're trying to write it too. First suggest that sigma I squared, okay, is equal to sigma squared is equals to sigma squared, okay, xi, I said si raised to the power beta, okay, si raised to the power beta, e raised to the power v, E raised to the power what? V. All right. So so we said that the test further suggests that sigma I square equals sigma square Si raised to the power beta E raised to the power V. Okay? In this case, the sigma from the right hand side is constant. The X is the variable or the predictor, that is the independent variable. Okay? E is some number, that is natural E. V is the error term. Okay? So you can answer that where sigma square is a constant, where sigma square is a constant. Okay, sigma square implies a constant. Okay, sigma I square is the unequal variance. Okay, sigma I squared represents the unequal variance. Okay, unequal variance. Alright, variance. Okay, the xi is the predictor variable, implies the predictor variable. Okay, or the regressor, or the independent variable. Anyone goes. Predictor variable. Where is it? Okay. All right. Then the V represents the error term. Okay. Error term or the random term. All right. So we have seen the definition of the equation given above. Okay. So now we can equally state differently the equation above by taking the natural log of both sides of the equation. The reason why we should do this is to linearize the equation above. For it is impossible for it to be solved normally without taking a natural log of what? Both sides of the equation. So that's what we put them in a linear form, or we put the equation in a linear form so that it can be manipulated. All right, so we now take the natural log of the sides of the sides of the equation given above, nonlinear equation given above. Okay, so that is, so now doing that we have the log. Well, we should know that natural log. Okay, we said that this. All right, let's say note that the log of base E equalizes the lane. Okay, lane. Okay, so in this case, we said that this L sub Ln means the natural log of what? Of any number of anything. Okay, so the base E makes it to be a natural log because the base E is a natural number. Okay, so doing that, we now have lane. We now take lane sigma I square, lane of the sigma I square. Okay, all right, equal to, now we begin, equals to the lane of the constant, that is sigma square. Okay, the lane of the constant. All right, that is sigma squared plus beta lane xi. Okay, plus beta ln si plus v, that is error term, plus v ln e. Okay. Now, since we said that that the log to the base e is equal to ln, at this point, from the right hand side, the v ln e, the ln e itself is unity, it's 1. Yes, because log of e, because log e base e is equal to unity. Okay, that is log of equal numbers. All right, so equal to ln n. Okay, so from the right hand side, okay, we have to substitute what in terms of ln e. We put what 1 there. 1 times v is v. Okay, so the equation reduces to what? Ln n sigma I square. Ln n sigma I square. Okay. Sigma I squared is really difficult to type in the 2, but bear with me. Okay, we have written the ln sigma I squared equal to ln of the constant. Okay, that's ln of the sigma squared. Okay, so all right, plus beta ln xi plus beta ln xi plus v. We have this stands as the error term. Okay, let's name this equation. Okay, let's call it equation A. Okay, so the equation above, okay, is the path test equation. All right. So having taken the natural log of the equation given above, okay, our nonlinear equation, having taken the natural log of it, okay, we have the linear equation in our equation A here. So we said that the equation, okay, A here is the path test equation. The normal equation in which we took the natural log is also the path test equation, but it was in a non-linear format. Okay, so we actually applied natural log, okay, rule, okay, to linearize the equation for us to have this equation A here. So the both equations are the path test equation, okay, which we are supposed to regress ln sigma I square, okay, on the predictor variable xi, okay. But for the fact that sigma I square is unknown in practical sense or in real sense, okay, so we have to not do with it well, so we have to do without it, okay, or dispose it, trying to look for the square of a residual, okay, in our normal regression, and substitute that in place of what? Sigma I square, so that we can able to what? Regress the square of the residual on the regressor. Okay, so now we can now say, okay, but the sigma I square is unknown. Okay, sigma I squared is unknown. Okay, is unknown, or is not known in real sense. Is unknown in real sense or in reality. Okay, so we have to substitute the square of the residual, okay, in it. Okay, so that is letting E, okay, where E represents the residual. Okay, now let's say what do we have here? Okay, let's say E cap. Mm-hmm. Yep. So, okay. Equal E. All right. So, you know what? Let's leave this. Okay. So, we now said we are less in E. Okay, squared. E squared to be equal to equalize sigma I square. Okay. To equalize sigma I squared. Okay. So where the E, where E square is the implies the square of the residual. At this point, we assume that the E alone is the residual. Okay, so squaring it, we have E squared. Okay, so normally we should have written E cap squared. Okay, showing that the cap there shows that the cap there shows that E is our what? The value of the residual normal. Okay, but we don't know how we can fix cap on top of E here. So we now say that E is our residual value. So squaring it, we have E squared, or the square of the residual. Okay? So now, then the problem is now, how do we derive this residual? First of all, before squaring it, that is the problem. Okay? So what we do is we establish a normal regression model. Well, our usual two variable regression model. Okay? So let's say, suppose we have a regression. Suppose we have a regression function as, well, a regression model as yi equal to a plus bxi plus let's say plus u, okay, or well plus e. All right. In this case, the e is the error term here, okay. But please, from that square, or let me call this u, please, okay. Let me represent this one with u, since I've given e as the value of the residual here. So let me represent the error term here as normal mu, okay, or u anyway, but mu. All right, so we have to regress y, or what? X, okay. Here we run the ordinary least square regression on the above equation, or on this particular equation given here, okay. Because we have said that usually in reality the value of sigma I square is unknown. Therefore, we substitute sigma I square with the square of the residual, okay, that is E cap square, okay, or mu cap square, all right, but we can't write cap here, okay, so we just represent that residual value with E, okay. So that is now say, okay, having regressed y on x, okay, we have our residual to be, okay, to be E. All right. So in this case now, we show that we are representing the value of our residual, in which we have derived from running a regression of y on x, okay, with e. Do you understand? That is, I mean that I should have represented our residuals value with e cap, okay, e cap, all right, having a cap on top of it, or e bar, okay, showing that it is the value of the residual. But we can't do that here, given the software I'm using, okay. But I said that I am representing the value of the residual with e, okay. The e is no more the normal error term, but it is the value of the residual, okay. So having regressed y on x, I have my residuals value to be what? E. So I'm going to square the e and substitute that in place of what? Sigma I squared, okay, since the e is now known, okay. So let's say we now let, okay, we now let the e squared, that is the square of the residual now, equals sigma I squared, okay, sigma I squared. All right, okay. So so now in the equation A, we have to substitute in place of sigma I squared, we put what? E squared. So now we now have ln n e raised to the power 2, okay, that is square of the residual, equal to, you have the same from your right hand side, ln of the constant, ln what? Sigma squared, ln sigma squared, okay, ln sigma squared plus beta ln x I, okay, plus v I. Okay, so well, let's call this equation B. Okay, so I just seen that the path equation has changed, okay. From the left hand side of the equation A of the same path equation, we normally have the variability in the variance of the error term, that is sigma I squared, okay. The I there shows a variability, okay, it's not a constant, okay. So since that is unknown, we regress a normal two variable regression, okay. We regress y on x, okay, and derive the residual, which we represented with e. Then we square it and substitute in place of what? E sub I squared, okay? That's ei squared, okay? So that gives us this equation below, okay? So we can now regress e squared on what? xi, all right? So we can now regress e squared on what? xi. That is meaning that we are running another regression, okay, on this equation B, okay? Trying to regress e squared on what? xi. After this, we test for the statistical significance of what? Beta, okay? And we do that by making use of the trace or T statistic of what? Beta. Okay, so now we now say regress the squared residual. We regress the squared residual on xi, on the predictor variable. Okay, now, okay, so, all right. So after we regress the square residual on xi and test for the significance of the beta, okay. All right. So how do we do this? We do this by observing the value of the trace statistic, okay, by, well, making use of T statistics, T stats of beta. All right. Okay. So now, when we regress E squared, that is the square of the residual on Xi, and we test for the significance of beta, we have to observe the value of the trace what statistics of the predictor what variable. Okay. Now, how do we do that? We really have to what check if beta turns out to be statistically significant. Okay, statistically significance. Then we say that there is what a variability in the invariance of the error term. That is, there is the presence of what heteroscedasticity in the regression model. That is, if beta is what significant. But if beta is not, then the null hypothesis is what accepted. Okay, that there is no what heteroscedasticity, or simply that the error term is what homoscedastic. Okay, so now said, having observed the value of the trace statistic, now so that if beta is statistically significant, then we reject the null. Okay, we reject the null of what homoscedasticity. Okay, yes. So because the alternative, I said that null is not true. Okay, since beta is what significance. Okay, so the H sub A, that the alternative hypothesis says that there is the presence of what heteroscedasticity in the model or in the error term. Okay, so we now say that if beta is statistically significant, then we say that the problem of unequal variance of the error term, exists. That is the presence. That is the presence of what? Heteroscedasticity. Okay, heteroscedasticity. Okay. All right. So conversely, like we have said before, I said that if beta turns out to be what? Statistically significant. Okay, we said that there is a problem of what? Heteroscedasticity in the error term or in the model. Okay, but if the reverse is the case, that is, if beta is not significant, if beta is not statistically significant, then the null hypothesis of homoscedasticity is what's true. Okay, then you can say then there is no presence of what? Unequal variance of the error term, or we can say that then there is, okay, then the error term, okay, or you said then the error term is homoscedastic. Okay, then the error term is homoscedastic. Okay, so that is what we mean normal. Okay, so Actually, in a model, before you estimate, okay, we have to check if there exists the presence of what? Heteroscedasticity. Because when there exists the presence of what? Heteroscedasticity, it means that the error term and the one of the predictor may what? Correlate, okay? Though the estimation, okay, after the estimation of the coefficients, okay, we may have unbiased what? Coefficients, okay. It may be consistent, but it will not produce a minimum variance, okay. So it is not best linear unbiased, okay. So for that reason, we have to use basically the PAC test, okay, to check if there is a presence of what? Heteroscedasticity in the error term of the regression model, okay. If there is this, then we try to what? Remove it using what? Our GLS, okay, that is the generalized least square, okay, or WLS, that is the weighted what? Least square, okay, to remove that, okay, so that we can have a blue estimator, okay. So, nevertheless, there are some criticisms, okay, in this test, PAC test, okay, there are some what? Criticisms, okay, in it, okay. Some people say that even in the PAC equation where we have V as error term, that even the V may still be what? Heteroscedastic, okay? All right, so that gave room, okay, to the development of what? Many other what? Tests, which we will do in our subsequent what? Tutorials, okay? Thank you. Thank you so much for watching. Bye, Makasi Chinedu. Please subscribe to my YouTube channel and watch our various videos in mathematics, econometrics, economics, and quantitative economics, okay? The name is what? Makasi's Academy. Thanks for watching.